Good afternoon, dear colleagues. I ask you to sit down and we start our afternoon session of the conference. The first speaker of the conference of the afternoon session is Mahender Singh from the Indian Institute of Science, Education and Research. So, Mahender, do you hear me?
Yes, I can hear you.
Please, you can start.
Okay. Thank you, Timur. Good afternoon, everyone. So first of all, let me thank the organizers for giving me this opportunity. Okay. So I wish I were there in Sochi and could enjoy the local thing. Nevertheless, next time. So today I'm going to talk about idempotents of quandle rings and enhancements of link colorings. So some small applications of the theory of idempotents in quandle rings and algebras that we worked on recently. So this work is based on a couple of papers that initiated with Valery Bardakov and late Professor Pasi, and then with Mohammad Ilamdadi and his students at USF. Okay, so let me just, for potential students, recall basics, a couple of basic facts. So quandles are algebraic structures with binary operations satisfying some axioms which are modeled on the three right-dimensional moves of planar diagrams of knots and links in the three space. And more than that, these objects are intimately related to what are called set theoretic solutions to the Yang-Baxter equation. And it has been a program that Vladimir Drinfeld envisaged to classify all set theoretical solutions to the Yang-Baxter equation. So ever since he wrote that survey article, a lot of research has gone into that. So what is a set theoretical solution? Is basically a map from a Cartesian product x cross x to x cross x, which satisfies this braid equation in this form, where Rij is a map from threefold Cartesian product to itself, which act as R on I and jth coordinate and as identity on the third one. And it's easy to see that a quandle also satisfies such an equation. So more precisely, a quandle is a non-empty set with a single binary operation, which we write as A star B, with three axioms. The first axiom is the idempotency axiom, x star x is x for all x in x. And the second axiom is that it can be restated in the way that right multiplication by each element is a bijection of the set. Okay. And the third one is the right distributivity. So x star y star z is same as x star z star y star z. So these axioms are in some sense just algebraic formulation of the three right-dimensional moves of planar diagrams of knots and links in the three space. So how to see that? So if you take an oriented diagram, so if you set a positive crossing, for instance, this, then we can set the rule that the over arc y act on the incoming arc and the output is what is the outgoing arc. And similarly for a negative crossing, we just put the star inverse. So what is star inverse here? Recall that the second axiom says that the right multiplication by each element is a bijection. So therefore, each element has an inverse with respect to right multiplication, and we can define a dual binary operation where we say that x star z is y if and only if x is y star inverse z. Once we set this convention, it's a direct check that the right-dimensional one move gives this that the arc x on itself is and the output is x star x. But since we want this arc to be same as x, that implies that x star x is x. That is exactly the right-dimensional the quandle axiom 1. And similarly, one can check that the right-dimensional move 2 is equivalent to this identity that x star y star inverse y is same as x, which is just saying that right multiplication by x by y is a bijection of the set. And similarly, the third right-dimensional move amount to right distributivity, that x star y star z is same as x star z star y star z. So this connects these objects intimately to knot theory. And how do we associate a quandle to a knot or a link? So we take an oriented knot diagram and define this object qk to be the quandle which is freely generated by the arcs in that diagram, modulo the relations, and the relations are precisely what I explained in the preceding slide. So at over arc, you said this kind of relation that y act on x and the outgoing arc is exactly x star y, and y act on the incoming arc at negative crossing and the outgoing arc is x star inverse y. So when we go modulo this, the object that we get, what we call the fundamental quandle of the corresponding knot or link. And for instance, if you look at a trivial n component link, so it has no crossing, so it has just bunch of these closed arcs, so it has n generator and no relations. So this is a free object in the category of quandles. In fact, one can give a precise description of this. This object is isomorphic to, you look at the free group of rank n and take the set of all conjugates of the free generators in this free group, and that equip that set with the binary operation of conjugation. So that is precisely a model for the free quandle of rank n, which is isomorphic to the link quandle of the n component trivial link. So it was a fundamental result of Sergei Matveev and David Joyce independently that this is a very strong invariant of knots and links. So given two oriented knots k and k prime is equivalent to k or the reverse of its mirror image if and only if the fundamental quandles are isomorphic. Okay. In fact, I could have just stated it for non-split links. The theorem statement is true, in fact, for non-split links. So what are the sources of quandles? Of course, as we saw that knots and links are the primary source, the topologically motivated sources of quandles. But one can also cook up these objects from a variety of other objects. I will list two, which just for the sake of motivation. So given a group G and an automorphism, we can define this new binary operation like this. And it's an elementary exercise to see that it's indeed a quandle. And if you take G to be an abelian group, phi to be inversion, it gives a well-known class of quandles, namely Alexander quandles. And also in the case of cyclic group, it gives you what we call dihedral quandles. Another example which comes from topology is the following. Given a closed-oriented surface of genus bigger than or equal to 1, let Mg be the mapping class group, which is the set of isotropic classes of orientation preserving self-homeomorphisms. It's a very interesting group and a very active topic of study in the theory of surfaces. Let DG be the set of isotropic classes of simple closed curves in this. So we just take simple closed curves, homeomorphic copies of circle, and take their isotropic classes. And in this collection, I can define a quandle operation. Alpha star beta equal to T beta alpha. What is T beta? T beta is the Dane twist along this simple closed curve. Okay. So we rotate any curve along this beta, and that's a new curve. And this turns this set DG into a quandle that we call Dane quandle of the surface. So if we know a little bit of mapping class group theory, it turns out that this DG, this quandle is nothing but the conjugation quandle, is a subquandle of the conjugation quandle of the mapping class group, where the elements are conjugacy classes of Dane twist along these simple closed curves. So one can actually see it inside the mapping class group. So since it will be too much of deviation, I will not say more on this. So let us come back to the main topic of our discussion today. So quandle rings. So these objects were introduced in a joint work with Valery Bardakov and Ibas Pasi in 2019. So the construction is analogous to what we do for group rings. So take a quandle and we take an associative ring with unity, and let Kx be the set of all formal expressions of this form, finite K linear combinations of generators from X. And just for ease of computation, we denote the elements of this object as E sub X for each X in X, because sometimes our quandle will have a binary operation, and if you want to construct this ring, these two operations will lead to conflict. So we use this note. Instead of writing just as X, we write E sub X. Okay, and there is a natural product in this module, K module, namely just as group rings. So summation alpha X EX and summation beta Y EY is just this product, alpha x, beta y, E x star y. This in fact turns this K module into a ring, rather a K algebra, if K is a field, which we call the quandle ring or the quandle algebra. And our idea was to bring ring theoretic and representation theoretic techniques into trying to understand quandles. So there is a word of caution here. Even though our coefficient ring is associative, the quandle ring Kx is non-associative in general. Most often it is non-associative. Only the good situation is only when X is a trivial quandle. What is a trivial quandle? When X star Y is just X. Okay. Every right multiplication is simply the identity map. In that case, the quandle algebra turns out to be associative. Otherwise, it's always non-associative. In fact, it is not even power associative in most situations. All right. So one can identify the original quandle X as a subset of Kx via this natural map. So X goes to 1 times Ex, that is Ex. All right. And we have an analog of the augmentation map. So you take any element of this quandle algebra, which is just finite linear combination of this basis element, and the value under the augmentation map is just the sum of the coefficients. This turns out to be a ring homomorphism. And in fact, the kernel of this is a two-sided ideal, which we call the augmentation ideal of the quandle ring. So it turns out that this augmentation ideal actually detects triviality of the quandles. So this was an observation with Valery Bardakov and late Professor Pasi in our first paper. So if X is a quandle and K an associative ring with unity, then the quandle is trivial if and only if augmentation square is trivial. So let me come to the main topic of this talk for the rest of the 15 minutes. So in the theory of group rings, units are very important objects, central objects of investigation. And in fact, trying to find precise structure of the group of units in group rings is a hard problem in general. So here we have defined quandle ring, which are highly non-associative objects. What are the right things here? Of course, units do not really make sense here, although one can append an identity and try to do that, but unfortunately it doesn't lead to a beautiful theory. But it turns out that idempotents are the most natural objects that one should try to look here. So in general, computation of idempotents in ring theory is a very important problem. And it is well known that integral group rings do not have non-trivial idempotents. It's a result of Donald Passman. In contrary, we will see that integral quandle rings of all quandles have non-trivial, all trivial quandles have always non-trivial idempotents, and many non-trivial quandle also have non-trivial idempotents. So later on, we will show some result, we will justify this claim. So before that, let me set one small notation. So by an idempotent here, I always mean a non-zero idempotent. And as we know, an element is idempotent if U square is U with respect to the product in this ring, and let I of Kx denote the set of all such non-trivial idempotents. Okay. A non-trivial idempotent. So observe that every element of the quandle is an idempotent by default, because X goes to Ex, and Ex square is E of X star X, but X star X is X due to idempotency axiom of the quandle. So we already have a supply of idempotents, non-zero idempotents in our quandle algebra, namely the elements of the quandle. The question is, are there more? So before that, we define a non-trivial idempotent to be an idempotent which is not of the form Ex for any X in this. That means which has at least two basis members in its expression. So those are the non-trivial idempotent that we are looking for. So let us observe some obvious, make some obvious observations. Suppose you have a finite quandle, and Y a subquandle of that of cardinality more than one, at least two elements in Y, such that the size of Y is invertible in the ground ring. Then Kx has non-trivial idempotent. This is similar to groups. So in fact, take this element U, which is summation Ey Y in Y, and just take the average. Okay. And now because cardinality of Y is more than one, so this is a non-trivial element in the quandle ring. That means it is not a basis member. And when you square it up, the second axiom, which is that right multiplication is bijection, implies that this is in fact an idempotent. Furthermore, the augmentation map is a ring homomorphism. Therefore, its value on idempotent is restricted. Namely, it has to be 0 or 1. So using this observation, we observed in our second work with Valery Bardakov and Professor Pasi that if T is a trivial quandle, then we can give a complete description of its idempotents. Okay. In fact, they are simply translates of the augmentation ideal by a fixed basis member. So basically, if I want to write down the precise expression for these idempotent, what are they? They are simply convex linear combination of basis members, summation alpha I exi, where summation alpha I is 1. As we can see, the augmentation value of this object is precisely 1 because delta k sub t is the augmentation ideal, which by definition are those elements whose augmentation value is 0. What are the non-trivial situations for us? So before giving a theorem, general theorem about non-trivial idempotent, we need to have some machinery. So here is the idea of quandle covering. So this idea is motivated by the classical covering space theory for topological spaces and manifolds. And to my knowledge, it was first developed by Michael Azerman, where he developed a Galois theory for quandles. So in fact, he defined homotopy groups and so on for quandles using this notion of quandle covering and show that there is a Galois correspondence similar to what we have for topological spaces or manifolds. So what is a quandle covering? It is a surjective group homomorphism, surjective quandle homomorphism, such that if you look at the fiber over a point, then the symmetry at those points are the same. That means the right multiplication by all the points on the fiber over a single point is the same. More precisely, Sx equals to Sx prime whenever Px equal to Px prime, where Sx is the right multiplication by the element x, which is a bijection by the second quandle axiom. So some basic examples come from plane group theory. So if we given a surjective group homomorphism from group G to H, then by functoriality, it induces a quandle homomorphism from the conjugation quandle of G to conjugation quandle of H. When is this a quandle covering? It is a quandle covering if and only if kernel P is a central subgroup of G. It's a direct check. Similarly, we have another construction of quandle, namely the core quandle, which is for abelian group, which comes from the second example that I mentioned in my second slide. So surjective group homomorphism from G to H gives a quandle covering if and only if kernel P is a central subgroup of G, but of exponent 2. And the third is a little rather artificial example. You given a quandle, you multiply it by a set viewed as a trivial quandle and look at the projection onto the first factor. This by very definition is a quandle covering because fiber over each point is the set X, which is a trivial quandle. So all the elements have the same symmetry, namely the identity. Okay. So there are plenty of quandle coverings one can cook up. And in fact, one encounters them quite often. So this is the main result that I wanted to state. So suppose that P from X to Y is a quandle covering. And let us say Fy be the set of all finite subsets of the base quandle. Similarly, for each Y in Y, let F of P inverse Y be the set of all finite subsets of this fiber. Denote a typical element of this set by Iy, one of the finite subset. Iy is a finite subset of the fiber over Y. So let us write E sub X bracket Y to be the set of elements, the set of basis elements that appear in the orbit of the element Sy. When you write multiply by Y, as keep raising the powers, you move this point Ex to Ex star Y, Ex star Y star Y, and so on, sum them up. This is the full orbit of this point Ex under the Sy action. With this notation, we have a complete description of idempotents for the quandle X, which is of finite type. So I say it is a finite type if these orbits are finite. So suppose that X is a quandle and P from X to Y is a non-trivial quandle covering, which is not not an isomorphism of quandles. If Ky has only trivial idempotent, so if the base quandle has only trivial idempotent, then I can give you the complete description of idempotents of the covering quandle Kx. In fact, sorry, there is a typo here. This is K. So the idempotents of Kx is precisely given by this formula. So what are these actually? So you have the base quandle Y, and what we do is you take the fiber over each point Y and take some convex combination over that. And over other fibers, you take those combinations which have zero augmentation value and take such sums. These are, of course, idempotent by very choice. It turns out that there is nothing more. These are all the idempotents. And the expression for the idempotents in the preceding slide tells you that each of those idempotent has augmentation value 1. So this made us make some conjecture. We did some computer calculations for quandles of order up to 7, particularly for dihedral quandles, and we observed the following. Any non-trivial idempotent of the integral quandle ring of a quandle has augmentation value 1. Always 1. This is what our computer calculations and also this theorem tells. So we believe this is the case in general. And furthermore, the integral quandle ring of a semi-Latin quandle has only trivial idempotents. What is a semi-Latin quandle? Where the left multiplication is also injective, not necessarily bijective, but injective. Of course, if your quandle is finite, then it is amount to lattice. It amount to being Latin quandle. In particular, our conjecture is that the integral quandle ring of a finite Latin quandle has only trivial idempotents. So again, we did some computer calculations for quandles of order up to 6, and it turns out that such quandles which are Latin, they have only trivial idempotents. So due to lack of time, I have only 3 minutes. I will skip this result and now come back to some application to knot theory in the last 2 slides. So there is a small, we made a small observation regarding usage of this idempotent in distinguishing knots. So let L be a link in R3 and QL is fundamental quandle. And suppose that X is a coloring quandle. Set of all quandle homomorphisms is an invariant because QL is itself an invariant. So this is an invariant and it's a classical invariant, namely the coloring invariant, which for dihedral quandles amount to the classical Fox coloring. A link invariant which determines the quandle coloring invariant is called an enhancement of the quandle coloring invariant. Furthermore, an enhancement is proper if we can find examples where the enhancements distinguish links, but which are not distinguished by the coloring invariant. Okay. So if you are given 2 quandles X and Y, we can look at the set of all K algebra homomorphism from Kx to Ky. Okay. And then we can prove this following, that if L is a link and X a quandle, then look at this tuple where the first one is the quandle coloring and the second one is the cardinality of algebra homomorphisms. This is a proper enhancement of the quandle coloring invariant. In fact, we can construct examples where the coloring does not distinguish, but if you go to algebra, you can distinguish. Here is the example. So consider the braid diagrams of these 2 links, L1 and L2 as drawn here. And when one does the calculation, one can see that the homomorphism from QL1 to R6, where R6 is the dihedral quandle of order 6, okay, has order 12 and same for QL2. But when you look at the algebra homomorphisms, I'm sorry, I forgot to write the number here. The numbers do not match. So we did the hand calculation and also ran a computer program. So it turns out that the set of algebra homomorphisms have different cardinality. In fact, one can give another enhancement of this. So here, in this theorem, I am using the algebra homomorphism. So now what I do is that I use the idempotents. That's the last result I want to say. Suppose L is a link and X a quandle, and let IKX be the set of all idempotents of the quandle ring KX, such that this itself is a quandle with respect to ring multiplication. then this ordered pair is a proper enhancement of the quandle coloring invariant, where the first is the number of quandle coloring and second one is also the number of quandle colorings, but the coloring quandle is now set of idempotents. And in fact, here the example below of link L1 and L2 shows that coloring does not distinguish them, but the coloring by idempotent distinguish them. Now, one might be wondering that we are putting too much restriction that the set of idempotent itself is a quandle. Does it really happen? Yes, that is what exactly our theorem tells. This theorem. So in this theorem, every idempotent of, So if you look at this set of idempotent, one can actually check that the set of all such idempotent actually is a quandle. So we have a quandle, we construct this quandle ring, and we look at idempotents in this quandle ring. Under good situations, it turns out that the set of all idempotent itself is a quandle, which contain your original quandle as a sub-quandle. So therefore, you can, instead of looking at homomorphism into your original quandle, you can also try to look homomorphism into your bigger set of idempotent, and it might help to distinguish two knots, which may not be able to, may not be distinguishable from the first coloring. So that was the last slide I wanted to present. I think I will stop here. Thank you for your time.
Thank you. Let us thank the speaker. We have time for one short question. Does anybody have it? I have it. Mahender, your talk was devoted to the study of idempotents in quandle rings.
Yes.
But in group rings, usually people study units. So does anybody study units of quandle rings?
So that's a good question. Thanks. So in our first paper with Valerie Bardako and Professor Pasi, we thought about this idea. So what we did, because there is no unit in this object, okay, quandle ring. Because if a quandle has a unit element, the only way possible is quandle has to be a trivial quandle with one element. So theory collapses. So the only way out is that you take the quandle ring or quandle algebra and append an extra element which you declare as identity. That's what we tried. And we gave some description of units, I think, for trivial quandles or R3, but it was not very elegant. But the question makes sense. I think if you look at some interesting quandles like dihedral quandle, it might be interesting. Maybe there is some interesting structure. Yeah, that's a good question.
I see. Thank you. So we don't have time anymore. I suggest to thank the speaker again.